class. So we were talking about the exponential distribution. And if I remember correctly, we were talking about something called the memoryless property, right? So we showed that last time that the exponential distribution is memoryless. But at this point, as far as we know, there could be infinitely other memoryless distributions. So what I wanted to talk about now is just the kind of a fact that I find pretty amazing, which is that the exponential is the only memoryless distribution in continuous time. In discrete time, we have the geometric. So in a very deep sense, the geometric is the discrete analog of the exponential. The exponential is the continuous analog of the geometric. So those two distributions are very closely related. So just to remind you, what the memoryless properties said, and also just because I saw some news article recently that completely misunderstood the concept of life expectancy, and that's not the first time that that's happened. So basically, it's a mistake of not understanding the difference between expectation and conditional expectation. Now, we haven't formally done conditional expectation yet, but I claim that you already know how to do conditional expectation because you just do expectation, except you use conditional probability instead of probability. But we talked about the fact that conditional probabilities are probabilities, so it's completely analogous. So we will spend a lot of time on conditional expectation later as a topic in its own right, but it's already something that's familiar, right? Just use conditional probability. Okay, so for this life expectancy thing, here's like the common misconception that I've seen in various news articles. Last time I looked, the life expectancy in the US was 76 years for men, 81 years for women. It's different in different countries and whatever. And it's kind of an interesting statistical problem. How do you actually come up with those numbers? So I'm not saying those numbers are exactly correct. I'm saying those are the latest numbers that I've seen reported. Now, how would you get those numbers? Because in principle, you think, if you want to know what's the life expectancy of a baby who's born tomorrow, right? Then I guess in principle, what you would do is take all the babies born tomorrow, wait until they all die, and then take the average lifetime, okay? Well, first of all, that's going to take over 100 years, and you might want an answer now. But secondly, at some point in time, you want an answer, right? But if you only look at the ones who've died up to that point and average those, that's going to be a very biased answer, right? Because you're ignoring all the ones who had longer lifetimes. Okay, so that's an example of what's called censored data. That's a good kind of censoring. It's censored because they're still alive. So anyway, that's a hard statistical problem and an interesting one. The reason I'm mentioning it now is kind of like good news and bad news about life expectancy. So let's just assume it's 80 years for simplicity. The mistake that I saw in this news article was basically assuming that it's like 80 years for everyone, including people. It was like about Social Security and Medicare, stuff like that. It was still assuming 80 years even for people who were already in their 50s and 60s. Okay, but the fact is, the longer you've lived, then your expected how long you're going to live total becomes longer. Okay, so if I wanted to write that as an equation, I would say, for example, if we let t be how long someone's going to live, given that person lives to be at least 20, that's going to be greater than just the expected value of t. It's kind of intuitively clear, so that's a conditional expectation. It just means given this information, and we compute our expectation based on conditional probabilities rather than unconditional probabilities, this should be pretty intuitive, right? That the case where that would not hold would be if everyone lives exactly the same lifespan, then this is irrelevant information. But as soon as there's variability in that, given that you lived this long, that's a good thing. So that's the good news. The bad news is that human lifetimes are not memoryless, right? People get older and decay with age. And so this is just to illustrate what the memoryless property would say. If human lifetimes were memoryless, it would say, and if the average is 80 years, then it would say if you live to be 20, then your new expectation is 100, right? Because it says, memory list says you're good as new, right? So you get an extra 80, no matter how long you lived, you get an extra 80 years on average, and that's not true empirically, okay? So the memory list property would say, I'll say if memory list, because that's not realistic for human beings, but it's realistic in some other applications. If memory list, we would have, I just want to translate what I just said into an equation. It would say that E of t given t greater than 20, well, you have those 20 years plus you're as good as new, so you should get an extra E of t. That's what the memory list property would say. Okay, so the truth is somewhere in between. So we actually have upper and lower bounds at this point. It's going to be somewhere between E of t and E of t plus 20. Okay, so that's the memory list property. So of course you could ask, since it's not very realistic for human beings, why do we care so much about it? Well, first of all, it's used a lot in different like science, chemistry, physics types of applications. It's sometimes used in economics. In some applications, basically it's realistic in problems where things don't decay with age. Or another way to think of it, like there's a homework problem about doing homework problems. And there's sort of two types of homework problems, roughly speaking. One is a type where just like you have to do a certain calculation, and you do the calculation and then you're done, and it sort of takes a fixed amount of time. Or at least that you can make partial progress, right? Then there's another type of homework problem where you could just stare at it for hours and have absolutely nothing, right? And then at some point, eventually, you have to be very determined, very persistent. At some point, you get this aha moment, you get the breakthrough, and you get it, okay? So memory list would be sort of like you can't make partial progress. Either you get it eventually or you don't. Whereas another type of problem, it's more of a fixed, gradual progress until you finish the problem. Okay, so there are cases where it's realistic, but the other big reason for studying it is that it's a building block. So if you go in and study what distributions do people actually use in practice for something like this capital T survival time, the most popular distribution that's used in practice is what's called the Weibull. And you don't need to know Weibulls right now, but just to mention it right now, a Weibull is just obtained by taking an exponential to a power. And as soon as, like if you take an exponential random variable and then cube it, that's not going to be exponential anymore. It's not going to be memoryless anymore. That's called a Weibull. It's not going to be memoryless anymore. And that actually turns out to be extremely useful. So exponentials are a crucial building block. But in some cases, memoryless, is not an unreasonable assumption, or reasonable. It may be a reasonable approximation, even if it's not exactly true. Okay? So that's just the intuition of the memoryless property. We proved that it was true last time for the exponential distribution, but now let's show that it's only the exponential distribution that has that property. So I'll state that as a theorem. So if x is a continuous random variable, and we're thinking about applications like lifetime, survival time, so we're thinking of positive valued random variables. So I'll say positive, that is, it takes values from 0 to infinity, with the memoryless property. So the memoryless property is a property of the distribution, not of the random variable itself per se, but we would say that the random variable has the memoryless property if its distribution has the memoryless property. Okay, and then the claim is just that it has to be exponential. So it's exponential lambda for some lambda. So this is a characterization of the exponential distribution. Okay, so now let's try to prove this result. And it's kind of an unusual proof compared to most that you've probably seen, because we're going to write down an equation, but we're solving for a function, not solving for the variable. So it's what's called a functional equation. Okay, so let's let capital F be the CDF, as usual. But as we saw last time with the exponential distribution, it's easier to think in terms of 1 minus the CDF for this kind of problem, because that's the probability of surviving longer than time t. So that's the CDF of x. And let's say g of x equals the probability that x is greater than x. So that's just 1 minus the CDF. So it's easier to do this problem in terms of g of x. Now, the memoryless property says in terms of g is easy to write. It's just the equation g of s plus t equals g of s, g of t. And we saw this. I'm not going to repeat the argument for this because it's the same thing as we did last time for the specific case of the exponential. Just write down, memoryless property is defined in terms of a conditional probability, but just write down the definition of conditional probability, and just in one line you can rewrite it like this. Notice this is true for the exponential, right? Because e to the minus s plus t is e to the minus s, e to the minus t. Okay? So we basically want to show that this is not like a usual equation where we're like trying to solve for s or solve for t or something like that. We're trying to solve for g. That is, we want to show that only exponential functions can satisfy this identity. Okay? So the way to approach this kind of equation is just to start plugging some stuff in and try to learn more and more about g. So we're trying to solve for g. And it's not like something where, oh, just plug into the quadratic formula or something, and then you just solve for g. We're trying to solve for this function g. So we just got to try to gradually learn more and more stuff about g, right? Okay, so the first thing I can think of, so this has to be true for all positive numbers s and t. Okay, so let's see, what can we learn about g? Well, one thing I can do is let s equal t, just to see what that says. Okay, so if we let we can choose s and t to be whatever we want, so may as well derive some consequences of this. So one choice would be let s equal t, and then that says that g of 2t equals g of t squared. I just rewrote that. Okay, so that's nice to know. What else can we see? Let's try g of 3t. G of 3t, well, I could replace s by 2t. That would be g of 3t. G of 3t equals g of 2t, g of t. But we know g of 2t is g of t squared, so this is g of t cubed. We can keep repeating that, formally by induction, but just repeat a few of them and you immediately see the pattern. Okay? So we immediately have that g of kt equals g of t to the k if k is a positive integer. So that seems like a useful property to know. Now, what if we went the other way around? What if we want to know what's not g of 2t, but g of t over 2? Well, actually, if I take this equation and replace t by t over 2, because this is true for all t, so I can plug in t over 2 for t, that's g of t over 2, and that's g of t. Take the square root of both sides. Then we get that g of t over 2 is the square root of g of t. Similarly, g of t over 3 is the cube root of g of t, and so on. So now we've figured out that this equation is true if k is a positive integer or if k is the reciprocal of a positive integer. Okay, well then the next step would be what if k is a rational number? That is, a rational number by definition is just a ratio of integers. So let's say we had g of m over n t. Well, if we just apply these two properties, that this is true, I'll write this one as g of t over k equals g of t to the 1 over k, where k is a positive integer. If we apply these two properties, then we immediately get that if we multiply by any rational number, the same thing holds. That's g of t to the m over n. So this m over n is any rational number. Okay? Now now if we have any real number, we can always treat a real number as a limit of rational numbers, right? Well, like pi, you could approximate pi You could say that pi is the limit of the sequence 3, comma, 3.1, comma, 3.14, comma, and so on, right? So you can pick a sequence of rational numbers that converges to pi, or any number you want. So just take the limit of both sides. Imagine, replace this m over n by a sequence of rational numbers. Take the limit of both sides. We're using the fact that capital G is continuous. Continuous means that if you take a limit of something like this, you can swap the limit and the G. So by continuity, this is true for any positive real numbers. Let's say g of xt equals g of t to the x for any real x greater than 0. Just by taking the limit of rational numbers, we can get real numbers. Okay, now we're basically done, because this is true for all x and t, so to simplify it, let's just let t equal 1. If we let t equal 1, this just says that g of x equals g of 1 to the x. That looks like an exponential function. In particular, let's write it in terms of base e. That's the same thing as e to the x log g of 1. So this thing, now g of 1 is a probability. So g of 1 is clearly between 0 and 1. If you take the log of a number between 0 and 1, you'll just get some negative real number. So this is just some negative number here. So we could call this thing minus lambda, where lambda is a positive number. This is just a constant, right? So I'm just calling it minus lambda. It happens to be a negative constant. So that's just e to the minus lambda x, which is 1 minus the CDF for the exponential. So that's the only possibility, okay? So exponential is the only continuous memoryless distribution. That's the proof of that fact. Okay? So we'll use the memoryless property and more stuff with exponential distribution from time to time. But there's another kind of key tool that we need at this point. You'll need it for the homework, and you'll need it in general, and that's called the moment generating function. So let's talk about moment generating functions. Moment generating function, which sometimes seems mysterious at first, but if you think carefully about what it means, you'll see why it's useful and what it actually means. Moment generating function, which we abbreviate to MGF. It's just another way of describing a distribution, rather than CDFs and PDF. MGF is another alternative way to describe a distribution. So the definition is that a random variable x has MGF m of t equals the expected value of e to the tx. This is as a function of t. And we say that it exists. This is not a useful concept unless this thing is actually finite on some interval around 0. So we would just say if this is finite on some interval, let's say minus a to a, where a is greater than 0. It could be that this thing is finite for all numbers t, which is great, but we're not requiring that to be true, but we are requiring at least having some tiny interval about 0 on which this is finite. All right, well, this definition at first seems to come out of nowhere, I think, and students sometimes really wonder, what's t? What does t mean, okay? So the first thing to understand about this is that this letter t is just a dummy variable, right? Conventionally, we call it t, but we could have called that s or q or w or anything else that wouldn't clash with the rest of the notation, right? I wouldn't have called it e or m or capital X, but anything that doesn't clash is fine. So t is just a placeholder. Secondly, what does this thing actually mean? Well, this is a well-defined thing because for any number t, we talked many times about the fact that a function of a random variable is a random variable. So that's a function of a random variable. That's a random variable. We can look at its expectation. That doesn't yet show why we would want to do that, but we can do that, right? So this is a function of t. That is, for any number t, we could imagine computing this expectation. So it's a well-defined function of t. It might be that it's infinity for some values of t, okay, but at least it's something we can write down and study. Okay, so think of t as kind of like a bookkeeping device. All the MGF is a fancy bookkeeping device for keeping track of the moments of a distribution. So let's see why that's true. So why is it called moment generating? Well, to see why it's called that, all we have to do is say, oh, we have e to a power here. Let's use the Taylor series for e to a power, right, which we've been using many times. So if we expand this thing out, expected value of e to the tx, that's the expected value, just the Taylor series for e to the x, that's x to the n, t to the n, over n factorial, n equals 0 to infinity. This is always valid, because the Taylor series for e to the x converges everywhere. X is a random variable, but this is always true. So that's a valid expansion. Now, intuitively, at this point, we want to swap the e and the sum. And that's where some technical conditions come in. In particular, that's where this fact matters, that we have this interval, n equals 0 to infinity. So just suppose for a second that we can swap this sum and the e. Then we would get this thing, e expected value of x to the n, t to the n over n factorial. This thing here, e of x to the n, is called the nth moment. So the first moment is the mean. The second moment is not the variance, unless the mean is 0, but the second moment and the first moment are what we need to compute the variance, right? And then there are higher moments, so that's called the nth moment. And higher moments have different interpretations that are more complicated than mean and variance, but they turn out to be useful for a lot of reasons. So assuming that we could do this swap, bringing the e inside the sum, then what we've really done is just captured all the moments of x into this Taylor series, right? So that's why it's called the moment generating function, because you see all the moments are just sitting there in the Taylor series. As far as showing why you can swap the e and the sum, if this were a finite sum, that would just be immediately true by linearity, right? Since it's an infinite sum, that requires more justification, and for that kind of justification, either you need to take a certain real analysis course or Stat 210, so I'm not going to try to, we need some more analysis and math to do that. But this is valid under the fairly mild assumption that we can do that this exists on some interval like that. So it turns out that we can swap. It's kind of like an infinite version of linearity, right? Swap the e in the sum, and we get that thing. Okay, so that's called the moment generating function. Now, I guess this shows that it would be useful if we were interested in the moments. But what if we don't care about the moments? I mean, usually we might care about the mean and the variance, but we haven't yet worried that much about higher moments than that. So let me just tell you 3 reasons why the MGF is important. Okay, so why is the MGF important? Well, the first reason is the moments. That's what we just talked about, because sometimes we do want the moments. So if x, so we're going to let x have MGF capital M of t. If necessary for clarity, we might subscript the x here, but right now we're just talking about one random variable. Here's its MGF, so it don't need a subscript. So the nth moment, that is e of x to the n, there's 2 ways to think of it. One, the nicer way is that it's the coefficient of t to the n over n factorial in the Taylor expansion of m. about 0, so a Maclaurin series, if you like. That's what we just showed over there, assuming we could do that swap. Another way to say this, just remember from your basic Taylor series from intro calculus, that to compute the, if you have some function and you want to compute its Taylor series, what do? You take the sum like this, and right here in this circle place, you put the nth derivative evaluated at 0, right? That's just how you do Taylor series, right? Take derivatives evaluated at 0. So another way to say it is that it's the nth derivative, which I'll write like that. So if we want the first moment, we could take the first derivative evaluated at 0, and so on. Okay, so it's the coefficient, and it is this thing. I'll just write that equals e of x to the n again, just for emphasis. So to get the nth moment, we could take the nth derivative of the MGF, evaluate it at 0. But as we'll see, sometimes it's a lot easier to just directly work out the Taylor series by some other method. For example, we already know the Taylor series for e to the x, right? Rather than going through like take derivative, take derivative, take derivative. Just write down the Taylor series. Okay, so that's the first reason. Second reason, which is probably even more important, even if we don't care about, the other two reasons are important even if we don't care about moments, okay? The second reason is that the MGF determines the distribution. So another way to say that would be, if you have two random variables, x and y, and they both have the same MGF, then they must have the same distribution. So if x and y have the same MGF, then they have the same distribution. For example, same CDF. If they're continuous, they have the same PDF, and so on. Then they have the same CDF. This fact is very difficult to prove. So I'm not going to try to prove this, but it's useful to know. If you compute some MGF and you recognize, oh, that's a Poisson of 3 MGF, then you can conclude that that's a Poisson of 3 random variable. There isn't some other distribution that kind of pretends to be a Poisson of 3, has the same MGF. Right? Once you know the MGF, you know the distribution, at least in principle. Okay, and then the other reason why they're important, aside from 1 and 2, is that they make sums much easier to handle. So we've dealt a little bit with sums of random variables before, and we'll deal more with it later. In general, finding the distribution of a sum of independent random variables is complicated. That's called a convolution. But if we have access to MGFs, things are a lot easier. Convolution, you have to do this convolution sum or convolution integral, which we'll deal with somewhat later. We've done a little bit of it before. It's complicated. But suppose we have MGFs. So let's say if x has MGF m sub x, and if y has MGF m sub y, and they're independent, then we want the MGF of the sum. A lot of times we're interested in sums of random variables, right? Just adding things up comes up all the time. Then the MGF of x plus y well, by definition, it's the expected value of e to the t x plus y. That's e to the tx, e to the ty. And we haven't proven this yet, but this is another fact that we're going to prove soon, that if we have expected value of two things, a product of things that are independent, then it's the product of the expectations. Okay? So we haven't shown that yet. That would be false in general if they're not independent. So it's crucial that we have independence or some other condition here. But we'll prove that later, that if they are independent, I'm writing this as e to the tx times e to the ty. Since x and y are independent, then e to the tx and e to the ty are independent. And according to that fact, then I can write e of the product as the product of e, using that assumption. But then notice that that's just the product of MGFs. So that's mx of t by definition, mx my of t. So this is really simple in the sense that if we have both of those MGFs, we just multiply them, right? We didn't have to do an integral, we didn't have to do some complicated sum, we just multiplied the two MGFs. So that's really convenient, okay? Let's do a couple quick examples of MGFs for specific distributions. So the easiest example to start with is Bernoulli, right? Bernoulli is the easiest, simplest distribution. So let's just start with the Bernoulli. So if x is Bernoulli P, then the MGF, m of t, equals the expected value of e to the tx. Now, we could use Lotus, but we don't even need Lotus here because we could just say e to the tx, x is just 0 or 1. So e to the tx is either e to the t or 1, right? Only two possibilities. The probabilities of those two cases are, with probability p, it's e to the t, p e to the t, and with probability q, it's 1, where q is 1 minus p, as usual. So I'm just taking a weighted average of the two possible values. It's either e to the t or it's 1. So just take a weighted average. So that's a really easy calculation. But because of that, now we can immediately get the MGF of the binomial because well, if we write down the definition, then we're going to have to do some big Lotus thing. But we don't have to do that because if we think of the binomial as a sum of IID Bernoulli P's and use fact 3 there, then we immediately know that the m of t equals the MGF of a Bernoulli to the nth power. So we just write it down immediately just by taking the nth power of that. Okay, so for practice, you could check. Remember, the binomial has the mean of the binomial NP is NP, and the variance is NPQ. And if you want to check that statement 1 there is true, you could take this thing and check that the first derivative evaluate at 0, you'll get the mean. Second derivative evaluate 0, you'll get the second moment. From there, you can get the variance. Okay, so that's the binomial. One more that we need right now is the normal, and that's a bit more of a bit more involved of a calculation. So let's let z be standard normal. Notice that once we have the MGF of the standard normal, then we know the MGF of any normal we want, because remember this thing about location and scale. So once we know this answer, MGF, then we could take any normal we want and go mu plus sigma z, figure out its MGF in a straightforward way, and that's good practice to make sure you know how to do that. So let's just talk about the standard normal first, because that's simpler. And we want to compute the MGF. So by Lotus, this is 1 over square root of 2 pi integral minus infinity to infinity. So we want the expected value of e to the tz. So by Lotus, it's e to the tz. And then we just have to write down the standard normal density, which is e to the minus z squared over 2. I already put the normalizing constant out there. So just minus z squared over 2 dz. That looks like a pretty nasty integral. But we will bravely try to do it anyway because we want to know the answer. So that looks kind of nasty. Now, if t is 0, then that's just 1, because then it's just saying integrate the standard normal PDF, we get 1. So we know how to do it without this linear, right? We have a linear term, we have a quadratic term. It's only the linear term that's annoying here, right? Without the linear term, this is just really easy. It's not easy, but it's one that we did, so it's easy given what we've done before. So the question is just how to get rid of the linear term. Well, then you have to think like all the way back to algebra class. How do you solve quadratic formulas, stuff like that? Completing the square, right? Something you probably thought you'd never see again, because once you know like the quadratic formula, you rarely bother to complete the square anymore, right? But that's what we need here, because if we complete the square, then it's going to look like a quadratic and not look like a linear thing anymore. Okay, so we just need a little bit of algebra. So this is e to the minus 1/2. Let's see if I can complete the square correctly. And we can factor out a minus 1/2. We attempt to complete the square. Well, it's going to be z minus t squared, I think. And then I have to adjust it. I'm just trying to do some algebra here. And it's hard to do algebra on the board, but let's try. So we have this thing, and then we need to fix it. But let's see if this gets at least the beginning right. If we multiply this out, it's e to the minus half z squared. That's good. Then we have minus 2tz times negative 1/2, so that matches this. And then the only part we need to fix up is this t squared. So this is going to be minus t squared over 2. So if we also multiply by e to the t squared over 2, and I'll do that on the outside because that's just a constant with respect to z, then that's going to cancel out that part. So that's just completing the square, dz. It's just algebra. But by writing it this way, it's much nicer than this because now we don't have this linear term anymore. Right now it's just something squared. Okay? All right, so what's this integral? Yeah, root 2 pi. Because, well, and if we include this part, then we get 1. That's just a normal. So this is e to the t squared over 2. This is exactly if we include the 1 over root 2 pi, this is exactly the normal. We recentered it at t. We didn't change the variance. Okay, so we're integrating a normal density. We must get 1. So just by recognizing, oh, that's a normal, except centered at t rather than centered at 0, we immediately know that's 1, so we get e to the t squared over 2. And from this, you can derive the non-standard normal as well, which you should do for practice. Okay, so we're going to come back to MGFs later and use them. But I want to do one more kind of like famous probability example that's not exactly related to MGFs, but which will be useful for the homework and for what we're doing next. And that's called Laplace's rule of succession. A famous old problem. Laplace was a great mathematician and physicist. And so there's this calculation that he did. And he phrased it in terms of what's the probability that the sun will rise tomorrow? Okay, so suppose that the sun has risen for the last n days in a row. And suppose we've observed we've been alive for n days. Every day the sun came up, n times in a row, right? What's the probability that the sun will rise tomorrow? And he kind of got ridiculed for working on that problem, partly because it seems like kind of crazy thing, and partly because the assumption is that we're considering random variables x1, x2, blah 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 blah. IID Bernoulli P, where think of those as the indicators, random variables for the sun rising on the first day, the second day, and so suppose that each day the sun either rises or it fails to rise, probability P that the sun rises, IID Bernoulli's. The other thing that's kind of fishy about this is that well, I mean, I have never experienced a day where the sun didn't rise, but if I did, then I start thinking probably like, that's, the end of the world, and it's not going to rise the next day either. So it doesn't seem very realistic to assume that they're independent. But it's still, it's kind of fun to think about the problem in those terms. That's just one story, and you can easily think of other problems that have the exact same structure as this. So even if you wouldn't apply this to the actual question of the sun rising, it's just a useful structure. So this is something we've dealt with before, just IID Bernoulli trials. Okay, but the twist to this problem is that Laplace is saying the probability that the sun rises is unknown, so P is actually unknown. And the question is, how do we deal with that unknown P? more precisely, let's say given P, this is true. If P is known, we're assuming this, okay? So all of this is conditional. This is conditional independence, okay? This is all given P, we're assuming they're IID, okay? But now we're saying, well, we don't know, right? We have evidence that the sun has risen n times in a row, but we don't know for sure what the value of P is, right? So we're going to treat P as unknown. And then kind of one of the, deep philosophical debates in statistics is how do we deal with unknowns, right? And for many decades, there's been this controversy between Bayesians and frequentists. That's a big topic for like 111, and not something we'll talk much about here. The question is, how do we deal with the fact that this P is unknown? Well, the Bayesian point of view is to say, well, since it's unknown, we're going to quantify its uncertainty by treating it as a random variable that has some distribution, okay? That distribution is just a reflection of our uncertainty. So the Bayesian approach is treat P as a random variable, and then use Bayes. The reason it's called Bayesian is because then we can use Bayes' rule to say, what's the distribution of P given all the evidence we have, right? So we start with some prior beliefs about P. That is, before we have any data or any evidence, we have some prior uncertainty. Then we collect data and we use Bayes' rule. Remember, Bayes' rule is how do we update based on evidence, okay? So update using Bayes' rule, and then we have some new uncertainty, okay? So that's the idea. So this is going to look a little bit strange because we're not used to treating lowercase p as a random variable, but this is just good practice and just thinking carefully about what random variable means. All right, so now we're going to treat p as a random variable, and we're going to say Laplace said let p be uniform. Of course, you don't have to use a uniform, but Laplace, and this is also a bit controversial. Like so this is called the prior. That's also a bit controversial, right? Like why uniform? Well, Laplace basically said, well, uniform should reflect complete uncertainty, just completely random. We know nothing about P, okay? But there are definitely some controversial issues about that. Well, let's assume that for now. So the structure of the problem, and let's let Sn be the sum of the first n of them. Okay, so here's the structure of the problem. The structure is that Sn given P is binomial. That is, if we condition on P, this just means treat P as a known constant, which is what we've been doing most of the time, but not always. This relates back to the problem about the random coins and things like that, right? The difference between independence and conditional independence. So this is just another example of that. If we know which coin we have, if we know the probability of the sun rising, then the assumption here is that it's IID. And so the sum of IID Bernoulli P's we know is binomial NP. But P itself is random with a uniform distribution. That's the structure, okay? And now the problem is to find, first of all, find the posterior distribution. By definition, posterior distribution means the distribution after we collect the data. This part is the prior, and the posterior is P given Sn. As we assume we observe S. You could also assume that you observe x1 through xn, and it turns out that you would get the same. This is what's called a sufficient statistic, which again is a 111 topic that you don't have to worry about per se. But it turns out that just observing how many of these are ones is enough. So we can condition on Sn, or we could condition on x1 through xn, and it won't matter. And the other question would be, what's the probability? The more practical question is, what's the probability that the sun's going to rise tomorrow? So that's the probability that xn plus 1 equals 1 given Sn equals n, let's say. So the sun has risen for the last n days. What's the probability that it will rise tomorrow? Okay, so that's what we want to do. So how do we do that? Well, the answer is just Bayes' rule. It's just that it's an unfamiliar form of Bayes' rule, but it's completely analogous. Okay, so to find this posterior distribution, I'm just going to write down something that looks exactly like Bayes' rule. Okay, so we want to find the f of p. I'm just using f to kind of generically mean PDF because p is continuous. Before we have data, we're treating it as uniform. Then after we have data, it's just going to have some density, a PDF, but it's conditional. Okay, it's a conditional PDF. So I'm calling that f of p given. Let's say given that Sn equals k. Okay, so that we're especially interested in the case where k is n. That is, the sun has risen for the last n days. But we may as well consider more generally, the sun has risen on k of the last n days. Okay, given that information, how do we update our uncertainty about p? It's just Bayes' rule. It's just a form that we haven't seen before, because on the one hand, these are PDFs. PDFs are not probabilities, okay? But PDFs, we can think of it kind of intuitively as a probability, or at least if we multiply by some, remember if we took a PDF times some little increment, then that's going to be approximately the probability of being in that little interval. So Bayes' rule, in this case, looks just the same as if you ignored the fact that that's a density, not a probability. So we're going to swap those two things. I'm going to say it's the probability that Sn equals k given p. The notation, it takes a little while to get used to, because we try, when possible, to distinguish between random variables and their values with lowercase and capital letters, but that's a little hard to do here because we let lowercase p be a random variable, and I don't want to start letting capital P be a random variable. So you can make up some new notation if you want, but it's easier to just think about what things mean. So this given p means we're just treating p as a known constant, even though it's a random variable. So Bayes' rule, we swap these things, times f of p, that's the prior, and it's also just equal to 1 because we used a uniform prior, so that makes it easy, divided by the probability that Sn equals k. This thing here in the denominator is an unconditional. This is conditional given p. This thing does not depend on p. It's not allowed to. This thing, in the numerator, it's a function of p. In the denominator, it does not depend on p. If we wanted to find it directly, we would use something that looks like the law of total probability. This is completely analogous to the law of total probability. This is the continuous version of the law of total probability, which we haven't done yet, so I'm doing it now, but it's completely analogous to the law of total probability. That if we want the probability of this event, then rather than doing a sum, we do an integral because it's continuous. We just do the integral of that given p, f of p dp. So that's a continuous version of the law of total probability. We don't actually need this, and I'm going to show you, we don't need it now, and I'll show you why. But I want to just tell you a little more about what this denominator means, okay? This denominator is a constant that doesn't depend on p. So let's just look at this thing up to proportionality. All right, that's a proportionality symbol. We're going to ignore the denominator because it doesn't depend on p, right? And for the numerator, that's just from the binomial. That's n choose k. N choose k is also a constant, as it doesn't depend on p. So I'm going to ignore the n choose k. That's just p to the k, q, 1 minus p, to the n minus k. Okay? So that part's 1. So that's actually easy. To get the constant in front, then we'd have to integrate this thing. And we're going to do that much later in the course. But now let's just do the easier case. F of p given Sn equals n. So that's the case where the sun did rise for the last n days. Now this is just p to the n. Now this one is easy to normalize, right? Because the integral of this from 0 to 1 is just p to the n plus 1 over n plus 1, so it's 1 over n plus 1. So to normalize it, we just stick an n plus 1 there. Now this is a valid PDF. Okay? And now lastly, to get this thing, so in other words, we got this thing without evaluating the denominator. And then lastly, if we want p of xn plus 1 equals 1 given Sn equals n, well, just think of it this way, that this is our, we want the expected value of a random variable with this by the fundamental bridge, we just want the expected value of a random variable with this distribution. So that's just going to be the integral 0 to 1 n plus 1 p times p to the n dp. Integral of p to the n plus 1 is p to the n plus 2 over n plus 2. So we get n plus 1 over n plus 2. So according to Laplace, if the sun rose 100 days in a row, then there'll probably be 101 over 102 for the next day.